First of all, let's just try to draw a diagram. So this is part of the hoop. And let's say the bead is over here. And we'll let this be equal to theta. So as it is sliding down, there is going to be gravity that's acting on it. And don't forget there's another bead that's sliding on the other side. And there's also going to be a normal force that's acting on the bead from the hoop. So both of these forces is going to create the circular motion that it's undergoing. So in order to find the upward force that is being exerted on the hoop, we need to find this normal force. And then to find that, we need to first find the centripetal force. So to find the centripetal force, we need the velocity. And to find the velocity, we can use energy. So the kinetic energy is equal to the decrease in potential energy. So we need this height over here. So let's just call the radius r for the time being. So mg r minus, so this entire distance is r, and this small distance is this r minus this section over here. And this section is just r cosine theta. And then we see that mv squared is equal to 2mgr 1 minus cosine of theta. And so we see that the centripetal force is equal to 2mg 1 minus cosine theta. And this is going to be equal to the net force that's acting on the particle. So using geometry, both of these lines are parallel, and so we get these alternate angles, they're the same. So in order to find the component that's pointing into the center of the hoop of gravity, that's just equal to mg cosine theta. So this is the force that's acting inside. And then we have a normal force that's pushing outside, so we minus n. So n is a function that can be positive or negative. When it's positive, it's pointing outside. If it's negative, it's pointing outside. So you can kind of imagine this being like the 3D coordinates. So you can imagine this being the x-axis, this being the y-axis, and then our z-axis will be pointing into the page. And then, so yeah, this will be kind of like the polar coordinates. And then our n is going to be positive if it points outside. So outside of the center. So rearranging this, you find that n is equal to, so we can pull the n to the other side, and then we have 3mg cosine of theta minus 2mg. And so this is equal to the normal force. And then also notice that this normal force, this is the expression of the force that's acting on the particle. And then we're interested in the force that's acting on the hoop. Well, the force that's acting on the hoop, let's call that n prime. That's just the negative of this, right? So note that the negative actually determines the direction of the force. So when it's sliding down, if the normal force is pushing outside for the particle, this is going to be positive, and this is going to be negative, which means the force is pushing into the center of this hoop for the hoop. So the force acting on the hoop is going inside. And so let us just write down what we have for the time being. So this is the expression, this function in terms of theta, of the amount of force that's acting on the hoop. So second of all, we're interested in the amount of force that's acting upwards, right? Because we want to find the condition where this upward force will not lift the hoop. So once again, we have a theta here. We just need to do a bit of geometry. And then we find that the vertical component is just multiplying the whole thing by cosine of theta. Now, observing this function here, you will see that if you draw a graph for it, you find that at theta equal to 0, this thing is negative, so you get 2mg minus 3mg, because cosine 0 is equal to 1. So we have something static and negative. And then if I let this angle be pi over 2, so pi over 2 is 90 degrees, so halfway through, you find that during this period, this from 0 to pi over 2, this expression here is going to change from negative to positive. And then once it reaches pi over 2, cosine pi over 2 is equal to 0. And because this whole thing is continuous, it's going to go up to somewhere positive and then go back down again. And then if you go from if you go further onwards from pi over 2 to pi, the cosine theta is always equal to negative. So this is positive, this is negative. So you get something that keeps going, that's always going to be negative. So you see that the upward force that's acting on the hoop, so don't forget that this is the force that's acting on the hoop. It should be pointing upwards. And then if it's positive, that means it's pointing upwards. If it's negative, that means it's pointing downwards. So in order to find the condition where the hoop will not be lifted, we need to find this maximum point. We need to find this maximum force that's pushing upwards. And to find that, of course, we need to use differentiation. So let's just be equally a function of theta. And we just do df d theta. So that's just 2mg negative sine theta minus 3mg, we have a cosine square, so 2 cosine theta negative sine theta. And then we let this be equal to 0, just as we always would when we're looking for extreme values of a function. So you plus 6 sine theta cosine theta equal to 0. So if we pull the sine theta out, we get 3 cosine theta minus 1 equal to 0. So you see your two solutions, cosine theta equal to 1/3, sine theta being equal to 0. So you know that this is kind of like a fake solution, so we don't need this because this only happens when theta is equal to 0 and pi, and we know that that's going to be negative. The force is going to be negative, so it's pointing downwards, so it's not the condition that we need. Well, for this, cosine theta equal to 1/3, this is going to be, this angle here is going to be this angle over here. So the angle such that cosine theta is equal to 1/3, this upward force is going to be maximized. So with this, we can set the condition such that when cosine theta is equal to 1/3, we want the upward force to be less than the downward gravity force, that's gravitational force that's pulling the hoop down. So now that we know that this is a condition where the upward force will be maximized, let's find the maximum possible upward force. So that's just that's just substituting cosine theta equal to 1/3 to this expression over here. So we get minus 3mg, so 1/3. And there's another cosine theta, so it's 1/3. And then don't forget, in the original problem, there are 2 beads that are rolling down. So for all our calculations here, we need to multiply this by 2. So the same force is going to be exerted from both of the particles from either side. So we get 2mg minus mg. So this is the maximum upward force that's going to be acting on the hoop. And then we want this to be always to be smaller than equal to the gravitational force that's pulling the loop downwards. And then don't forget, in our original question, what we're looking for is the condition for m, small m over big M, such that the hoop never rises. So that small m over big M must always be smaller than 3/2. So g's cancel out. So in other words, the mass of the particles must be smaller than 3/2 of the mass of the hoop. So this is the condition.